Hello. The next talk is Finding and Exploiting 20-year-old Bugs in Web Browsers by Fratric from Google Project Zero.
All right. Welcome, folks, to Finding and Exploiting 20-year-old Bugs in Web Browsers. I know it's late in the day on the second day of the conference, so I am really grateful for all of you who found patience to listen to yet another talk. My name is Ivan Fratric. I am at Google Project Zero. I've been doing this security research thing for quite a long time now, and one thing I like to do besides just to do security research is to write and publish tools to help me, but also potentially others with their security research. So if you happen to use these tools and if you happen to find them useful, I would really love to hear about that. Otherwise, if you haven't seen those are mostly specialized tools for black box binary fuzzing, for structured fuzzing, and sometimes both at the same time, as we are going to see a bit later. So our story today began sometime last year when I was browsing social media, minding my own business, and I stumbled across this blog post about a vulnerability in web browsers where the author used XSLT in web browsers to leak local files. Now, I know this slide mentions ChatGPT, but don't worry, this is not going to be an AI talk. I won't do this to you this year, at least. We'll see about next year. But this year, we are doing classic vulnerability research. Instead, when I read this, I didn't think about AI, but I thought rather, do we still have that XSLT thing in the web browsers? So that got me thinking, where else have I seen that recently? And indeed, there was an issue a couple of years ago, back in 2022 in Firefox. And in fact, it was not just any issue, it was an issue that was exploited in the wild. And while we are on the topic, we really can't be talking about XSLT security without mentioning amazing work done by Nicolas Gregoire, who over a number of years published different techniques, different tools, different vulnerabilities. So in case you are interested in the topic of XSLT security, his work is definitely something that you should read up on. But for my part, I'm really wondering why we still have XSLT in web browsers, because it seems like one of those features that in this day and age is primarily useful as attackers, as a source of vulnerabilities, rather than for any legitimate use case. And I genuinely believed we don't have it anymore. And the reason I thought that we didn't have it anymore was, well, I couldn't remember what the reason was, but I searched for it, and then I found an intent to deprecate and remove it in Chromium all the way back in 2013. Well, obviously it didn't happen. And the reason it didn't happen was because, I kid you not, 0.02% of all page loads use XSLT. And that can be a very low number or a very high number, depending on how you look at it. But in either case, we are stuck with this XSLT thing in the web browsers for the foreseeable future. So might as well take a look, right? For my part, last year I had some moonshot projects that didn't quite work out as well as I hoped. And so I was looking to do something more along the lines of a classic vulnerability research project, you know, back to basics kind of stuff. And I encountered all of this XSLT stuff. And even though I've been doing vulnerability research for a long time now, I never actually looked at XSLT, so I decided that was a good target. So now let's take a look at it together. So what is this XSLT thing anyway? Well, I was chatting earlier today with Eduardo, and he had a pretty good description for this, which was an OG templating system. Basically what XSLT is, it's a templating system for XML, where you give it an XML file, a source XML document, you give it a style sheet with some templates, and then based on this style sheet, it transforms the source document into the destination document. And the very common use case for this is to transform XML into HTML that you can then render in your web browser. And in order to really explain or say anything about XSLT, I really need to mention XPath first, because XPath is used everywhere inside XSLT. And what XPath is, in case you didn't encounter it before, it's like a SQL select statement, but for XML. So for example, if you have an XPath expression /foo/bar, what this does is it selects all bar nodes that have a foo node as its parent, and the foo node is also the root element of the XML document. So you can use these XPath expressions to select a subset of nodes from an XML document, and this will come up often later. So now with XPath done, we can take a look at XSLT again and how it actually works, because when I was searching for information about XSLT, you often find documentation about its various features, but you rarely see how the transformation is actually done. What's the process for transforming the document? So I'm going to quickly run through how it works. So basically how the process goes is you first start traversing the source document, and then for any node you encounter, you check if you have a template that matches this document. And in this case, we have a template that matches the root element of the XML, which you can see from the /XPath expression. And then at this point, we apply the corresponding template to the element that matched it and its children nodes. And at this point, we stop traversing the source document and instead start traversing the elements inside the template, and we execute any XSLT instructions that we encounter along the way. So the first thing that we have in our template is actually not an XSLT command, it's just a normal XML element, and these by default we would just copy to the destination document. And then here we have our first XSLT command, which is the XSL for each element. And what this is, it is essentially a for loop over the elements returned, or in general, over the nodes returned by the XPath expression. So in this case, this is going to be a for loop over all item elements. And so then for each of these item elements, we again have like a normal XML element. We just copy it to the output. And then the next thing we have is our second XSLT command of the day, which is XSL value of command. And what this does is it just outputs the text of the currently selected element. So it's going to output the text of one of these item elements. And this happens for all of these item elements because we are doing a for loop over them. So what this does in summary is it transforms this source XML document with these items to an HTML list. And this is the simplest example that I could find to explain how this thing works in general. But this can get really complicated because you can have various XSLT commands. You can have various XPath functions that are only accessible from XSLT. And then you can have very complex expressions in XPath. You can also have things like variables, etc. So there is quite a lot of complexity here. And all of this complexity is exposed as an attack surface in web browsers. So in which ways is it exposed? There are actually two methods how you can reach this. The first is through XSLT processor JavaScript interface. And this is nice because it gives you a lot of control over what is going on, and you can invoke various functions from JavaScript on this XSLT processor interface. And then there is also the second method, which is if you simply navigate your web browser to an XML document, and this XML document has an embedded style sheet, well then the XSLT engine is going to apply that style sheet to the document before it gets rendered. And this is interesting from the attacker's perspective because it allows the attackers to reach this attack surface even if JavaScript in the web browser is disabled. In terms of how this is actually implemented in web browsers, there are two implementations that cover the majority of the browsers. The first is libxslt, which is an open source library which implements XSLT 1.0 or 1.1 standard. I'm not sure. So the reason why the majority of the web browsers use libxslt is a bit historical. Initially, only WebKit used this, but then when Blink, which is Chromium's DOM engine, got forked from WebKit, it continued to use libxslt. And now, of course, all the web browsers that are based on Chromium are also going to rely on libxslt. And so, in fact, the only other implementation, the only other browser that doesn't use libxslt is Firefox, which has its own custom implementation that is a part of Firefox's DOM engine. And these two implementations are quite different. And one way in which they are different is because libxslt is an open source library. It's a standalone library that lives independently of the browser and its DOM engine. So whenever the web browser wants to call into libxslt, what needs to happen first is you need to first convert all the data into the representation that libxslt can process. So in general, how this happens in Chromium is mostly through strings that then get parsed by libxml2, and then you end up with a representation that you can pass to libxslt. And this is quite different from Firefox, where the XSLT engine implementation is part of Firefox's DOM engine, and because of that, it operates on the same DOM node structures as the rest of the web browser. And I thought that was really interesting because this opens up a class of vulnerabilities where something unexpected could happen with those DOM nodes during XSLT processing. And speaking about the bugs, this is what is public so far. There might be more, there might not be more. I cannot say. But let's go with this is what is public so far, and already, as you can see with what has been published so far, we have full vulnerability coverage over all the major web browsers. And these vulnerabilities, these bugs, mostly fall into two categories. The first one are bugs due to unexpected things happening during XSLT transformation with the rest of the web browsers, such as unexpected interaction between JavaScript and XSLT. And those were mostly found either manually or through variant analysis. And then we also have another type of bugs, which are the bugs in XSLT implementation itself, which do not rely on any other component. And those were mostly found through fuzzing. Okay, so at this point, I think like the boring part of the talk is over, so we can take a look at some of those vulnerabilities that were found. So the first vulnerability that I'm going to show you, it was a vulnerability in Firefox's implementation of XSLT processor JavaScript interface. And if you looked at this implementation a couple of months back, then what you could see is that it had a member variable, which was a pointer to a document object, which was called mStyleSheetDocument. And so it represented, as the name suggests, the style sheet document. And here, in this declaration, what you could also see is a comment that says weak. But and this is a bit strange, because this comment weak implies that this is a weak pointer. But if you look at the declaration, it's not a weak pointer, it's just a raw pointer. So what is going on? How can it be a weak pointer? Well, it kind of is, or was, because XSLT processor registered itself as a mutation observer for this document. So what would happen is, before this document would get destroyed, this callback would trigger, and inside this callback, we would set the pointer value to null. So it does, in a sense, behave like a weak pointer, because a weak pointer is supposed to be set to null when the corresponding object gets deleted. Except there is an issue here, and the issue is with this part. And that is, the function can return early, and if the function returns early, well, then in that case, we don't set the value of this pointer to null. It is left dangling, and that leads to use after free vulnerabilities. This is the basic vulnerability here, but reaching this condition where this function would return early wasn't trivial. It required quite a few stars to be aligned, which fortunately was possible. But I'm not going to show you all the details in this presentation. I just want to focus on the things that I think are particularly interesting. All the details are in the corresponding Project Zero bug tracker entry if you want to read them. But one thing that I found interesting about this bug is that, well, when I reported it, one of the comments from Mozilla person looking into this issue was that it got introduced back in 2003. So in fact, this bug is kind of responsible for the title of this talk. And in fact, the bug predates Firefox 1.0. And well, if anyone had this bug, then this bug would give them quite a long time frame of ownage. That is, unless some pesky Project Zero researcher comes along and kills your bug. But I think this highlights a very large difference from XSLT as an attack surface and other popular attack surfaces in web browsers, because XSLT is so old and not much development is happening in that space, unlike, say, JavaScript engines, which change a lot. And so because of that, all vulnerabilities you find in this code tends to be quite old, and the vulnerabilities tend to be quite long-lived. So at this point, let's take a look at another vulnerability. And I think this one is, in my opinion, the most interesting one. So if you fell asleep during my explanation of how XSLT works, maybe now is a good time to wake up, because I think this is a really good one. And I really can't say that I'm the one who discovered it, because this was discovered through variant analysis. And at this point, I want to make a note on methodology, because one thing I noticed during my time doing security research was that I often found very cool things by looking at previous issues that on the first glance might not appear to be very critical. So take a look at this issue here, and imagine that you are searching for remote code execution bugs in the web browser. And looking at this issue here in the slide, it's moderate severity. It doesn't give you RC or anything like that. So looking at previous issues, you might skip it, or at least I might skip it in some parallel universe. But fortunately, in this universe, I did not. And it turned out to be really, really interesting. So really, honestly, kudos to the original reporter. So let's take a look at this issue. The first thing that was reported in this issue was that the author could prevent the tab process from exiting. And the way they did that was by exploiting the fact that XSLT transformation would continue running even if the tab or the window was closed. And you know, so far so good, but this isn't really groundbreaking. But then the reporter came back and said something else which I found really, really fascinating. They said, I was able to execute JavaScript code in a tab after the window was closed. And that got me thinking, right? If XSLT still running is what is preventing the process from exiting, and if they can run JavaScript during that time, does that mean they can run JavaScript during transformation? Because I can tell you for sure that the XSLT processor was not implemented with JavaScript running at the same time in mind, especially JavaScript running in the same context. So, but it turns out this was exactly what was happening. So let's take a look at how that works. So this is an XSLT style sheet. And inside this style sheet, you have an XPath expression, as you do. And inside this XPath expression, you call a special function called document. And this is one of those functions that are only accessible from XSLT. And what this document function does is it loads an external document. You can give it an URL, and if the same origin policy allows, then it's going to load the document from that URL. But loading an external document takes time, right? And Firefox wants to be efficient. It doesn't want to waste the time. So what does it do? Well, it enters an event loop. And during that event loop, it processes all the pending events, including some events that might have JavaScript callback. And in the simplest case, it can be even simpler than that. Simply, if you have a JavaScript timeout event, it might trigger during these document loads. So now the question is, with this JavaScript running during transformation, and because XSLT is in because XPath is in XSLT everywhere, you pretty much get an universal callback that you can call at almost arbitrary points in time during XSLT processing. So now the question is, what can you do from that callback that would result in memory issues? And the answer to that is, well, pretty much everything you do during that callback that touches XSLT in any way is going to result in use after free vulnerabilities. So for example, if you delete a node from the source document during transformation, you get use after free. If you delete an element from the style sheet during transformation, use after free. Delete a variable, use after free again, etc., etc. So this really was something that could potentially give an attacker a very wide range of primitives to exploit. And now for the question of how and if it was fixed, which is a bit complicated, because I really can't say that it was fixed in a way that I would like. Because originally, when I reported this issue, what I hoped for is that it would be fixed by disabling JavaScript during document loads. But that didn't happen, because according to a Mozilla person working on the issue, disabling all JavaScript during these documents loads would be, quote, hard, unquote. And I can't really say I understand the reasons. But as it is, the current situation is that all the known instances of use after free issues, or at least all the instances that I knew about, are fixed. But the larger issue remains in the sense that you can still execute JavaScript callbacks during document loads. And so I was thinking about, well, is there some other way that this could be fixed more comprehensively? And the proposal I came up with was based on how Chrome does things, or rather how Chrome doesn't do things. Because in Chrome, if you invoke XSLT through XSLT processor JavaScript interface, this document function actually won't work at all. And so I suggested to Mozilla that they do something similar. And this seems to be the current directions that things are taking. This is currently implemented in such a way, which is, I think, a bit stronger than the original fix. But you know, disabling this document function results in regressions. So in the long run, how this turns out, we'll see, but this is the current status. So let's now stop talking about these manually discovered issues and say a few words about fuzzing. So I'm the author of a fuzzer called Jackalope, and Jackalope was initially developed as a black box binary fuzzer. However, it also has a sanitizer coverage mode for fuzzing open source software, so this is something that makes it also applicable for fuzzing XSLT implementations because they are all open source. But one thing that I think makes Jackalope especially applicable for this purpose is another feature, which is its mutational grammar engine. And this mutational grammar engine isn't new, but I consider it underutilized, and I also never spoke about it at the conference. So I consider it fair to say a few words about it. So originally, when I developed this mutational grammar feature, I developed it for fuzzing closed source JavaScript engines. And in that project, this grammar-based mutational approach performed quite comparably to Fuzzily. And now I'm not saying that this is going to perform comparably to Fuzzily in general case, because Fuzzily is a very specialized fuzzer for JavaScript, and these are old JavaScript. These were old JavaScript engines missing a lot of the features of the current JavaScript engines. But what I do want to say is that I consider this very effective way, a very effective approach of creating custom fuzzers for various targets where you don't really need to implement the entire fuzzer. You can just implement, you can just write a grammar. And the grammar format is quite simple. And if you ever used my other fuzzer, Domato, to fuzz web browsers, then you would be instantly familiar with the grammar format because the grammar format is very, very similar. So I wrote an XSLT grammar and used that to fuzz first libxslt, and this resulted in some vulnerabilities. And I was really happy with how it worked because some of the samples that triggered vulnerabilities were not trivial, and in fact they required multiple different features of XSLT to be put together in a very, very specific way to trigger them. So we have a sample here that triggered the vulnerability, so I'm just quickly going to run through it to explain what is going on. So the first thing that we have here is an XSL variable element. And what this is, it's essentially a global variable. So in style sheets, you can have global variables, and these global variables get evaluated before anything else does. And inside this global variable, we have an XPath expression again. And from this XPath expression, we are referencing another variable by name. So what this means here is that now from evaluating this XPath expression, we need to recurse into evaluating another variable. So we have another variable here. And if we start evaluating that, we encounter a for loop again, which iterates over all of the namespaces in the source document. And normally, when you evaluate an XPath expression, an XPath expression returns to you a subset of XML nodes, and it will return them to you by reference. But namespaces are special, because when evaluating an XPath expression that returns namespaces, some of the namespaces will get copied. So keep that in mind. And then from inside this for loop, there is another XPath expression that is a part of an XML attribute, and this is in XSLT. This is called attribute value template, and so here it's important to note that libXSLT is old, and because it is old, it's very conscious about memory. It tries to use as little memory as possible, and one of the ways in which it tries to save memory is it only has one XPath evaluation context object for the entire style sheet evaluation. And what's going to happen inside this XPath expression, which really doesn't do anything, but before evaluating this XPath expression, the current node of the XPath context is going to be set to one of those namespaces. And then when we finish with our for loop, those namespaces that got copied will get deleted, will get freed. But the issue here was that for these attribute value templates, the current node of the XPath expression won't be restored to what it was previously, and it will remain pointing to pointing to one of those namespaces. And so then, when we return from our recursion into the XPath expression that we recursed from, well, now our current node, which is referenced by the dot inside the XPath expression, still points to a freed namespace, a freed object, which, of course, results in a use after free vulnerability. So again, showing you this not just because I think the vulnerability itself is interesting, but just to demonstrate that the fuzzer needed to use different features of XSLT and put them together in a way that makes sense in order to trigger this vulnerability. And this and other similar issues weren't found on some huge fuzzing cluster. They were found on a single machine, which I think is another thing that demonstrates this mutational grammar fuzzing approach. So we can fuzz libXSLT relatively easily because it is an open source library. It's easy to just write a harness and fuzz it in isolation. But what about Firefox's implementation? Because, as I said, Firefox's implementation is a part of Firefox's DOM engine. It relies on other DOM objects. You can't easily just take it out and fuzz it in isolation. So how do we fuzz that? Well, fortunately, Firefox already has a pretty neat support for running mutational fuzzing engines. In particular, it has support for libfuzzer and AFL. And for all of these fuzzing engines it implements something called fuzzer driver. And this fuzzer driver is then an interface between a fuzzing engine and the web browser. So what I did is I implemented another fuzzer driver for Jackalope. And the patch to do that wasn't upstreamed, but I did publish it. So then if you take this patch and apply it to Firefox, and hopefully it still applies cleanly, you end up with Firefox that you can fuzz with Jackalope, with all of Jackalope's features, including, of course, this mutational grammar engine. And of course, I use that to fuzz libXSLT, but in a more general case, I think mutational grammar fuzzing approach would have other use cases to fuzz other interesting APIs inside a web browser. And this approach, again, resulted in a vulnerability. And I'm going to show you this vulnerability because it is in a bug class that is, I don't think it's very widely known. So, did you know that standard template library, C++ standard template library, implementations of sort and stable sort might not be memory safe? And in particular, one way in which they are not memory safe is if you are using a custom comparator function, and this custom comparator function does not respect what is referred to as strict weak ordering. Now, what is this strict weak ordering? Well, it's more complicated than that, but essentially it means that your comparator function needs to behave consistently. So if you have object A and object B, and A is less than B for whatever criteria your comparator uses, then your comparator always needs to say that A is less than B. And if you have stuff like A is less than B, which is less than C, then also A needs to be less than C, etc. And because XSLT is complex, it implements various functions, and one of the capabilities that XSLT has or needs to have is capability to sort XML nodes. And of course, for that, it needs a custom comparator function. And how this comparator function was not very consistent, you could already see on its first line, because what this first line essentially does is it says if any kind of error occurred anywhere in previous invocations of this comparator function, then the comparator function is always going to return -1 for whatever arguments. So of course, it's not behaving very consistently, and any kind of strict weak ordering just goes flying out of the window. So at this point, let's stop talking about vulnerabilities, and let's see how we can exploit one of those vulnerabilities. And the vulnerability I chose to exploit was that vulnerability in Firefox, where you could run JavaScript during XSLT, or more precisely during document loads during transformation. And the reason I exploited that vulnerability first was because it simply just gives the attacker so many different primitives an attacker can use. In terms of exploit structure, it really isn't anything groundbreaking. It first converts the bug into an info leak, and then after that we do a classic vtable replace. So I won't show you all the details, but again, I want to focus on the details that I think are particularly interesting. So we are going to take a somewhat closer look at the info leak phase, because firstly, often getting that initial info leak with DOM vulnerabilities is a bit tricky. But secondly, because this is going to highlight another vulnerability class that I don't think is very widely known. So the way I intended to convert this issue into an info leak is by converting a use after free into an out of bounds read. And the way I intended to do that was by exploiting the way in which Firefox's XSLT implementation stores DOM attributes. And specifically, the way it stores them is this implementation, when an attribute needs to be stored, is not going to store a pointer to a DOM attribute object. Instead, it would store a pointer to the element that contains the attribute, and then an index of that attribute. So then what you can think is, if you have a use after free scenario, you could free the element and then get it replaced with another element, and then but the other element has less attributes, and then if you try to access an attribute at an index which is now stale, that index is going to be out of bounds. So that gives you an out of bounds read, which you can use for various things, such as, for example, to read an attribute name out of bounds. So this was the idea, except there was a problem with that idea. Originally, I was reading just Firefox's binary code when I was working on the exploit, and I missed one thing. Because if you read the source code, you can clearly see that there is a bounce check when accessing attributes. And that bounce check is here. So it shouldn't work, right? Because this checks that whatever attribute index you are accessing is less than the number of attributes. Except the reason why I didn't notice this bounce check in the binary code was because this bounce check was not present in the binary code. It got optimized away. Now, why on earth would the compiler remove a bounce check? So let's look at what's going on. If the bounce check fails here, you can clearly see that the function returns a null pointer. But the issue is that the calling function does not check for null pointer, which means if the bounce check fails, that results in null pointer dereference. And now, the trick is the compiler knows that null pointer dereference is undefined behavior. And the compiler can prove that if in the case of bounce check failure, that always returns in null pointer dereference. And the undefined behavior basically gives the compiler the license to do anything it wants. And of course, what the compiler chooses to do is the stupidest thing imaginable, which is just to remove the bounce check altogether. So there you have it, folks, another bug class that might not be that widely known, which is that if you have a bounce check and failing bounce check results in a null pointer dereference and the compiler can prove it, then the bounce check gets removed. At least that is the case in the current version of Clang. So that was the info leak. And for the code execution part of the exploit, it really isn't anything special, just like a classic vtable replace. But one thing that I think might be interesting to talk about here is what kind of objects you can use to replace an object in Firefox's default heap, because some objects won't work that are classically used in exploits. So for example, array buffers or you can't use array buffers here because these would be allocated on a separate heap arena. And DOM strings, although you control most of the DOM string, actually at offset 0, DOM string is going to contain some things that you can't control, such as its size and flags. So you can't really use it to do a vtable override. So what I ended up using was a DOM blob object, which firstly gets allocated on the default heap, and secondly, the entirety of its content is attacker controlled. So this works well. Okay, so let's show that exploit. So what I have here is a Firefox that desperately wants to update and tries to tell me I'm a bad person for not allowing it to. I'm not sure if you can read this, but currently it's Firefox version 135.0, which is a version from, I believe, somewhere towards the beginning of this year. So relatively recent, but of course it does not include any of the patches for the bug that we will be exploiting today. And I should also note that I really didn't do anything special to make the exploit reliable. So it can fail, and this is a live demo. In practice, it does work relatively reliably, except when people are watching. In that case, it fails consistently every time. So let's see if I'm lucky this time. Okay, so we can point the browser to our exploit server, and the exploit has several stages, and it looks like the first one succeeded. And the second one succeeded. So now, there we go. All right. And in case you are wondering how am I popping a calculator with Firefox having a sandbox and all, I'm not doing anything special. This is a renderer vulnerability, but I did modify the config of this Firefox installation to allow certain syscalls from the sandbox that it normally does not allow. So, to wrap up, XSLT is an old attack surface. It's a complex attack surface, which is always a killer combination. And because it's so old, the bugs tend to be quite old as well. To find those bugs, to find the bugs in the XSLT engine itself, the mutational grammar fuzzing approach turned out to be pretty effective, but of course that only gives you a subset of issues because you also have issues that require interaction between the XSLT engine and other browser components. So that is all I prepared for today. I would like to thank you again for your patience. And if there are questions, I would love to hear them. Maybe I can even answer some of them.
Are there any questions?
Otherwise, you feel free to catch me today at the conference.
Hey, thanks for the great talk. So I was wondering, because we had this case with bounce check and null pointer check, right?
Yeah.
And this is actually not the first time this is happening here and there. So are there any flags or attributes you can use over this function that would prevent this from being optimized?
You can probably prevent it from being optimized, but there is also a compiler flag that you can use that actually Chrome does use that disables this particular optimization.
Is this the fno delete null pointer checks or something like that?
Something like that.
Okay. Yeah, thank you.
Thank you for your talk.